in real life, so there are many quantities you want to maximize. There are many quantities you want to minimize. Now, for instance, the quantity you want to maximize is probably, if you do business, profit, right? You want to maximize the profit when you do business. And also, there are many quantities you want to minimize. When you do business, you want to minimize what? The cost, right? Minimize the cost, maximize the profit. So that's how you do business. In next class, we're going to see some real life problems. But the real life problems are going to be converted to the problems like finding the maximum and the minimum of a function on some interval. So today we do the math part. Okay. Some definitions first. Okay. You imagine you have the graph of a function. We are going to use one graph to illustrate many definitions and many conclusions. Okay. You imagine the function is defined on some closed interval from a to e. So do you see point A? And do you see point E? Again, we treat the function as a function defined on the closed interval from A to E. The two endpoints are included. Okay. Now let's recall some terms you have seen in high school before. Okay. Now let's say on the interval from A to B. On the interval from A to B, if you look at the graph of the function, only on the interval from A to B, you'll see from the left to the right, the curve is going uphill, right? In this case, we say the function is increasing. And likewise, now let's say from B to C, on the interval from B to C. So do you want to tell me a term? How do you describe the function from B to C? I just want to make sure you are following me. From B to C, the graph is kind of going downhill, right? In this case, we say the function is decreasing. For the terms, if we have time, we are going to treat all these definitions rigorously. Okay. But now we just visualize the meaning so that you can see what's actually going on. And likewise, on the interval from C to D, the function is increasing again, right? It's kind of increasing as you're going uphill again from left to right. And then from D to E, the function is decreasing. Okay. I just told you the meaning of increasing, decreasing function on some interval, right? And then if you download the handout, I believe it's handout number 8. If you download the handout, in part 1, I give you a list of definitions and some conclusions. I will show you the meaning of the definitions and why some conclusions are true. It's not the proof. It's not the proof now. So later on, if we have time, we're going to prove them. But here we're just to try to visualize geometrically why the conclusions are true. Okay. You look at item number 1. In item number 1, we are trying to define what we mean by a function has a local maximum at some number. Okay. You look at the graph. You look at the point B on the horizontal axis. Point B, I want you to look at point B on the horizontal axis. You see when x is close to B and to the left of B, the function is increasing. Okay. And then when x is close to B and to the right of B, the function is decreasing. In this case, we say the function has a local maximum. the graph I copied, the author is calling it relative maximum, the same thing. Two alternative terms, you can say. We say the function has a local maximum at number b. Again, the location of the relative maximum or local maximum is b. We say b is the location, and the value of the maximum, you have to evaluate the function at b. I don't know the value, so actually the value of the function at b is not labeled. You could imagine, let's say, this point, the value of the function at b is some number. Again, I say b is the location of the local maximum or relative maximum, okay, and the value of the maximum is the value of the function at b. I want to repeat the meaning. Again, the meaning is when x is close to b and to the left of b, the function is increasing, and when x is close to b and to the right of b, the function is decreasing. In this case, we say the function has a local maximum or relative maximum at b. And likewise, you see this point c. You see this point c is actually a local minimum or relative maximum. I mean the location. C is a location of a relative minimum. So because to the left of, so did I say something wrong? So now let me try again. Okay, I was trying to say C is a location of a local minimum. So because to the left of C, the function is decreasing, and to the right of C, the function is increasing, right? So we say C is a local minimum. Okay. And likewise, D is a location of another relative or local maximum. It's because to the left of D, the function is increasing. To the right of D, the function is decreasing, right? So I told you the meaning of local minimum and the local maximum. Again, so do not be confused. We say the points like B, C, and D are the locations. To get the value of the maximum or minimum functions, you have to evaluate the function. A little bit more comments. Why do we call it a local maximum or relative maximum? It's only locally the value of the function at b is a maximum. It's like something, let's say, in this class, if you are the tallest in this class, you may not be the tallest at the college or high school, right? That's why we call them the local minimum or relative minimum or maximum. So that makes sense? Again, I was trying to define relative minimum and the maximum using in terms of increasing, decreasing of the function. Okay. That's one thing I want you to know. Okay. I told you the meaning of the definition on this slide already. Okay. Item number 1, I told you item number 1, and item number 2, what we mean by local maximum and local minimum. Actually, I really want you to see the property in item number 3 and item number 4 at this point, so do not look at handout. Do not look at handout, okay? Okay, now let's concentrate on the property of the function on the interval from a to b, maybe, okay? Again, we only concentrate on the property of the function from a to b. I told you the function is increasing, right? I told you the function is increasing on the interval from a to b. Now you listen to my question, okay? Try to answer my question. Can anybody try to use the property of the derivative of the function when x is in between a and b to describe? What can you say about the derivative of the function when x is in between a and b. I'm going to repeat my question, okay? What can you say about the derivative of the function when x is in between a and b? I told you the function is increasing when x is in between a and b. Now I'm looking for a description in terms of the derivative, why the function is increasing from a to b. Recall, geometrically, the derivative of the function at any number is the slope of the tangent line. The slope of the tangent line, okay. Okay, I'm going to ask you the question the following way, reversely, okay. Actually, if it's a real face-to-face class, I would ask people to wave their hands to tell me the shape of the graph. Now listen to me carefully, okay? Listen to me carefully. So tell me the shape of the graph. Tell me the shape of the graph if the derivative is always positive. So forget about the graph of that function, okay? On a new slide, tell me the graph of the function. Tell me the shape of the graph if the derivative is always positive. I will give you some hint. If the derivative of the function is always positive, then the slope of the tangent line at any number is always positive. By that we mean at any point, the slope of the tangent line is positive. The tangent line has so try again, please. So probably before we answer the question, you want to recall what we mean by what we mean by the slope of a line is always positive. If you have a line in that shape, the slope is positive, right? By that I mean from the left to the right, you are going uphill, it's positive slope. If you have a line in that shape, you are going downhill from the left to the right, then the slope of the line is negative. I believe you can remember that, okay? If the line is horizontal, the slope is equal to 0. You just use our common sense to understand the meaning of the slope. So like the pitch, right? Again, if you have this shape, the slope is positive. If the line is going downhill, the slope is negative, right? If the line is horizontal, the slope is equal to 0. Now let's go back to the question I just mentioned. The question I asked you was if the derivative of the tangent line at any number is positive. I want you to tell me the shape of the graph. So tell me a term. Okay, I will try to tell you the conclusion right now. I know it's kind of hard to imagine, but I'm going to tell you the conclusion right now. If the derivative is always positive, then the graph of the function, it has to be in that shape. You could check, okay? The derivative of the function is always positive. It means the slope of the tangent line at any point is always positive, right? At any point is always positive. At any point is always positive. Then the graph of the function is increasing. I mean the function is increasing, okay? I was trying to motivate the following conclusion. You look at item number 3, okay? Item number 3, so try to understand the meaning. If the derivative is always positive, greater than 0, it's always positive, right? For all the numbers on some interval, then the function is increasing on that interval. It means the graph of the function is going uphill. So does that make sense? Again, the bottom line is try to remember the conclusion, and also try to understand the meaning geometrically, okay? I was trying to say if the derivative of the function on some interval is always positive, then the function is increasing on the interval. And likewise, if the derivative is always negative, then the function is decreasing. In item number 3 and item number 4, we are trying to use the properties of the derivative to study the function is increasing or decreasing. And by the way, we are on another important topic about applications of differentiation. Okay. You see, the derivative is relevant to the graph of the function, right? When we do curve sketching, we are going to see the double derivative is also relevant to the graph of the function. Okay. I mean the shape of the graph of the function. Okay. I'm done item number 3 and item number 4. So of course, so later on we're going to use some particular questions to show you the meaning. But now I'm going to motivate another concept. Now let's concentrate on point D. Okay. We have seen the function has a local maximum. The function has a local maximum at D. For the people who came in late, it means the function is increasing to the left of D, the function is decreasing to the right of D. In this case, we say the function has a local maximum at D. Okay. Anybody want to tell me? Now you listen to me carefully. Anybody want to tell me how to use the derivative to describe what is? Now let me try again. Okay, what is the derivative of the function at D? What is the derivative of the function at D? You see, this point is not a corner point. It kind of says the function is differentiable at D, which means the function has a derivative at D. Using the geometric meaning I just told you, what is the derivative of the function at D? So geometrically, what is the derivative of the function at D? How do you want to tell me the tangent line? How do you want to tell me the tangent line to the graph of the function when x is D? You can give me a description of the tangent line. You look at the mouse cursor. How do you want to tell me the tangent line to the graph of the function at this point? It doesn't matter. So try to say something, please. So you know that. So don't be scared. The tangent line is horizontal. So that makes sense? My original question was, what is the derivative of the function at D? The tangent line is horizontal. The slope is 0. I was trying to say the derivative of the function at D is equal to, so tell me a number, please. The derivative is the slope of the tangent line. A horizontal line is 0. It's 0, right? Sure, thank you. Cool. I was trying to say, if the function has a local maximum or local minimum at a number, so 0 is right. If a function has a local maximum or local minimum at a number, now let's say D, then the derivative of the function at this number is equal to 0. Again, we have seen C is a location of a local minimum, right? The same is true. If I'm asking for, you see the graph of the function at point C is kind of smooth, no corner point. It means the function has a derivative at C. If I'm looking for the value of the derivative, is the slope of the tangent line to the graph of the function when x value is c, right? You see the tangent line as horizontal again, right? So the derivative of the function at c is also 0. Okay. I was trying to motivate the next conclusion. Okay. You look at item number 5. Now suppose the function has a local minimum or maximum at a number. If the function is differentiable, it means graphically it means the graph of the function is smooth at that point. We mentioned before, no corner point, no sharp points on the graph. And then the derivative of the function at c is equal to 0. We have seen that, right? We have seen item number 5. Again, at this point, I'm not going to rigorously prove anything, but I want you to see why the conclusions are true geometrically. Okay. Item number 6. In item number 6, we are trying to define what we mean by a function has an absolute minimum or maximum on some interval. When we define absolute maximum and absolute minimum, it has to be relevant to some interval. Okay. In most questions, the interval is given, or in some application problems, the interval can be found. Okay. But I think the definition is not too hard to understand. Absolute maximum, it just means the largest possible value of the function on the interval. I think it's labeled on the graph actually. Okay, you see the largest value of the function on the interval from a to e. The location is d. The value of the function at d is the largest when we talk about for all the values of the function on the interval from a to e. So we say the function has a absolute maximum, has the absolute maximum at d. And likewise, the function has the absolute minimum at a, right? You see the value of the function at a. I mean the point on the graph is the lowest, so which means the function has the absolute minimum at a. In other words, a is the location of the absolute minimum, and d is the location of the absolute maximum. Later on, we are going to be able, for almost any function, we are going to be able to use differentiation to get to compute the absolute maximum, absolute minimum. In many cases, relative maximum, relative minimum on some interval. Okay. But at this point, all these questions are designed to, the graph is designed to understand the meaning of the terms. Okay. One additional question. How can you tell me about, so now let's say in terms of the derivative of the function, what is the derivative of the function at b? I will try to make the question a little simpler. Okay, you see the function has a relative maximum at b. What can we say about the derivative of the function at b? You see it's a sharp point, right? A corner point. I mean, when x value is b, the corresponding point on the graph is a corner point, right? In this case, we say the function is not differentiable. You remember the term? We did quite a few questions like this, right? Now I'm trying to tell you the possible locations of relative or local maximum and the local minimum. What are the possible locations? You see C is a location. The derivative of the function at C is equal to 0. We have seen that, right? And D is a location of a local maximum. You look at the mouse cursor. D is a location of a local maximum. And the derivative of the function at D is equal to 0. And B is a location of a local maximum. The derivative of the function at B does not exist. So DNE, right? Now I'm going to motivate the next concept. Actually, for any given function, when finding the locations of local maximum or local minimum, the first thing you do is to determine the possible points. All possible points are called critical numbers. I'm going to motivate the definition of the critical numbers. The term of the critical numbers are possible locations of local maximum and the local minimum. Okay. What are the possible locations? The possible locations are the values of x at which the derivative is equal to 0, or at which the derivative dne does not exist. I will show you the next definition. After this one, we are going to be able to do some questions. Okay. You look at item number 7. Okay. If the derivative of the function is equal to 0, or the derivative is undefined, actually a better wording is dne does not exist. If it's one of the two cases, and then we say C is a critical number. I want to repeat, a critical number is actually a possible location. Now let me try this way. The critical numbers are the possible locations of local maximum and the local minimum. I want to repeat. Critical numbers are possible locations of local maximum and the local minimum. For all the items on this screen, on this slide, of course, we need to do some questions to fully understand the meaning of everything. Okay. So do you have any questions so far? Now we are ready to work on some questions. And by the way, I forgot to mention one other comment. Okay. I think not all people agree on that, but now let's agree on that. When talking about the local maximum and the local minimum, the two endpoints are not included. By that we mean we never say A is a location of a local minimum or local maximum. We never say E is a location of a local maximum or local minimum. Okay. And one other comment. Okay. One other comment. The critical numbers, I said, are possible locations of local maximum or local minimum. Can I add one more point? So now let's say A, B, C, D, E. So can I use A1 to denote this point? Sorry, I cannot write white on white. I'm going to use A1 to denote this point. It's because I do not want to use F. F is a common notation for functions, right? I'm going to use A1 to denote that point. Actually, this point is actually a critical number. I'm trying to say the derivative of the function at A1 is equal to 0 as well. But A1 is not a location of a local maximum or local minimum. I'm trying to say the derivative is equal to 0 or the derivative does not exist. These are the conditions of the possible local maximum or local minimum. You have to use some other properties to confirm these locations are indeed the local maximum and local minimum. Now, for instance, x value of A1 is a critical number. but it's not a location of a local maximum or minimum. Okay, you're going to fully understand everything after we do some questions, so don't worry. Okay. Are you ready? Now let's work on some questions. Okay. Now question 1, it's possible to solve this question using high school math. You see it's the function is essentially the graph of the function. The function is a quadratic function, right? You know the graph is a parabola. And in high school you have learned many properties about the parabolas, right? I'm trying to say it's possible to find the absolute maximum of the function on that interval using high school math. And probably you could do it by completing square and stuff, but now we are going to have a way more sophisticated way to get the absolute maximum. We are going to use the derivative. Okay. When we do this question, I will give you the step procedures. Okay. Now the solution. I think I'm still on red. I'm going to use the simple question to show you the step procedures. The first thing we do is to differentiate the function. So because we want to get the critical numbers, right? In step 1, so should I write some wording? So differentiate the function, okay. We're doing applications of differentiation anyway, right? Differentiate the function, so they think it's going to be useful. We're going to see how they think it's going to be useful. The derivative of the function is super easy, right? It's 4x. Actually, it's 4, right? The derivative of 1 is 0. The derivative of 4x is 4. And then minus 2x. Okay. That is the derivative of the function. And then in step 2, we are looking for the critical numbers. Can I just write find the critical numbers in step 2? I want you to recall the definition of the critical numbers. You are looking for x values. You are looking for at what x values the derivative is equal to 0, and at what x values the derivative dne does not exist. So anybody want to tell me the critical numbers? I believe you can see it. At what x values the derivative is 0 or dne? Yeah, 2 is right. Okay. In general, after differentiating the function, you solve the equation, you let the derivative be 0. So because you want to solve the equation for x, at those values of x, the derivative is going to be 0. Okay. I'm trying to say to find the critical numbers, you let the derivative be 0. And then in this particular case, you have an equation of x. The derivative is 4 minus 2x, right? Equals 0. And then it's easy to solve that equation for x. Isolate the terms involving x. Probably you want to write in this form: 4 is equal to 2x. And then you divide two sides of the equation by 2, so you have x value is 2, right? This is the only critical number. This is the only critical number. I'm trying to say that's the only possible location of a local minimum or local maximum. and I'll say the only critical number. I was trying to write a number. I think you know what I mean. Okay. And one other thing I want to mention, after getting the critical number, you do need to make sure the critical number is on that interval. So because for most questions we're looking for the minimum, local minimum, local maximum, absolute minimum, absolute maximum of the function on some interval. Okay. In this particular case, the interval is given. You have to make sure the critical number found is indeed in that interval. So that makes sense? We said earlier, actually, in this case, the critical number is just a possible location, the possible location. Okay, to convince it's indeed a location of a local maximum or absolute maximum or minimum, you need to do something else to convince yourself. What else? So do we need to do? The next thing we do is to form a table. So how about you just concentrate on how to form the table first, and then after I tell you the meaning of the table, everything so will be clear. Okay. In step three, we're going to form the table. Okay. Form a table. Form a table of the following form as follows. I do not want to write too many forms. As follows. I will tell you how to form the table. Okay. How to form the table. Label the columns. Okay. You see, the function has only one critical number. The critical number is 2, right? And you have seen 2 is on the interval from -2 to 5. You kind of treat -2, the interval from -2 to 2 to 5 as the domain of the function. I know the domain of the actual function is all the real numbers, but in this particular question, you just treat the domain as restricted. Okay, the domain is restricted from -2 to 5. Okay. To form the table, I mean to label the columns, to give the thing in the first row, you think 2, the critical number, in this particular case, one critical number. Okay, you think one critical number will divide the domain of the function into how many subintervals. If you do not see what's going on, you try to draw a number line. Okay, in this particular case, the number line is, let's say the origin is here. Let's use that point as the origin. Okay, the origin is here, so -2 is here. You could use a circle to indicate -2 is not in the interval. Okay, and now let's say 5 is here. Sorry, it may not be too proportional. So now let's say 5 is here. Okay. Again, we have only one critical number. The critical number is 2, right? Now let's say 2 is here. To get the first row, I mean to get the column titles, to get how to label the columns, you think, listen to me carefully, you think the critical number divides the domain of the function into how many subintervals? Into 2 subintervals, right? One subinterval is the subinterval from -2 to 2, and the other one is from 2 to 5. Okay, that's how you get the column titles, or that's how you label the columns. In the first row, I forgot already. I think I still remember that. You're right. Again, you think the critical number divides the interval into how many subintervals. This will give you the subintervals. The subintervals are from -2 to 2, right? And also from 2 to 5. Okay. In general, leave leave that bracket open. I'm trying to say the subintervals to form the subintervals do not include 2, do not include the critical numbers. You're going to see why later. Okay. That's how you get the first row. So in general, if you have many critical numbers, you can imagine you think many critical numbers will divide the interval into how many subintervals, right? And then there could be many subintervals. Okay. After getting that, after getting the first row, you get the columns. Okay. Always label the first. The second row. The second row. Always label the second row using the derivative of the given function. Now what we are trying to do is to use the derivative of the function to study the property of the function. Okay. And label the next row using the function. So temporarily, you just remember the form of the table. Very shortly, I will tell you how to get the content of the table and how to use the content of the table to determine if 2 is indeed a location of local maximum or absolute maximum or minimum and so on. Okay. So okay. Probably it's easier if I copy the derivative onto the next slide. The derivative of the function is 4 minus 2x. Right? I will tell you how to get the content of the table right now. Okay. So this thing is not part of the solution, but I'm going to need this. So basically, the next thing we do is to determine if the derivative on that interval, on the interval from -2 to 2, is positive or negative. By that I mean in the second row. So can I call that row the second row? In that row, you look at the mouse cursor. In that row, I'm going to need the signs, positive or negative. Okay. Now listen to me. It's another super important point. As long as you get all the critical numbers properly, as long as you divide the domain into the subintervals using all the critical numbers, it's always safe to use the test numbers to determine the signs you need in the second row. Okay, now for instance, you look at the mouse cursor. Okay, I'm not going to move the mouse cursor now. At this location, I need to determine if the derivative is positive or negative on the interval from -2 to 2. Okay. Now all we need is to use a test number. Can anybody try to tell me what number you want to choose from the interval from -2 to 2? Any number. Try to choose the number as simple as possible. Choose a number in between -2 and 2. So -1 is good. -1 is good. Okay, why not? But so 0 is better. 0 is simple, right? When using 0, it's easy to evaluate anything as 0. So how about we just use 0? Okay, or using -1, the same thing. So why not? So we use -1. Okay. In order to get that sign, that question mark is going to be a sign, positive or negative. In order to get that sign, you use a test number. So Danica told me using -1. Now let's use -1. Okay, we compute the derivative of the function at -1. Okay, and then we have 4 minus 2 times. 2 times -1. So what number do you get? I think you have positive 2, right? Sorry, you have positive 6. I'm not good at numbers. You have positive 6, right? You have positive 6. Actually, I do not care about the values. I just care about the number is positive or negative. Okay. When you see the value of the function at any number on that interval is a positive number, you write a positive sign in here. Okay. If you want to convince yourself, you can choose any test number on the interval. I told you before, as long as you get all the critical numbers properly, as long as you divide the domain into subintervals properly, it's always safe to use the test numbers to determine the sign. By that I mean, if the derivative of the function at one number on the interval is positive, then the derivative of the function at all numbers on the interval is positive. It's always safe to use a test number to determine the sign. Okay. So anybody want to tell me a test number on that interval? On the interval from 2 to 5? Any number on the interval. Choose a simpler number. So maybe 3, right? 3 is on that interval. Choose 3. Okay, and then you evaluate the derivative of the function at 3. So by that we mean it's 4 minus 2 times 3. I believe you have -2, right? You have -2. So which is negative? By that we mean, sure, thank you. 3 is good. By that we mean the derivative of the function on that interval, on the interval from 2 to 5, is negative. I want to repeat, it's always safe to use a test number, to use any test number to determine the sign of the derivative of the function on the interval. Okay. Actually, the thing on the left is not part of the solution. You do that on scratch paper. Okay. What I need is a table. Okay. We have seen the derivative of the function is positive on that interval, on the interval from -2 to 2. The derivative of the function is negative. Did I say something wrong? So now let me try again. The derivative of the function is always positive on the interval from -2 to 2. The derivative of the function is always negative on the interval from 2 to 5. Now what can you say about the function on the interval? If the derivative of the function is always positive on that interval, what can you say about the function on that interval? Recall the conclusion we just mentioned earlier. If the derivative is always positive on some interval, then the function is increasing, right? That's where I need that conclusion. In the future, you can use that notation to denote that the function is increasing. So that makes sense? Now you see, essentially we are trying to use the derivative of the function, positive or negative, to determine if the function is increasing or decreasing on the interval. So that's the whole idea, right? Okay. And likewise, so because the derivative of the function is always negative on the interval from 2 to 5, so the function is decreasing on that interval. Okay. I know there are too many things coming on at once, but I hope the thing is not too hard to understand. I know it's possible for you to use the high school math. You even know the graph of the function. It's possible to sketch the graph. But Uh, Now I want you to kind of imagine the shape of the graph. Do not use your high school math. Forget about all the knowledge you learned about the problem or quadratic functions. So do you see the function is kind of in that shape? So now let's say, so 2 is here, 2 is here. To the left of the 2, from negative 2 to 2, the function is going up. It's increasing, right? And to the right of 2, the function is decreasing. So do you see 2 has to be the location of the absolute maximum? So that makes sense? I want to repeat. It's because to the left of 2, you look at the table. To the left of 2, the function is always increasing. To the right of 2, the function is always decreasing, right? The graph has to be kind of in that shape. It's probably curved, okay? Which means 2 has to be the location of the absolute maximum. You see how the table is useful, okay? And then in item number 4, we are going to draw the conclusion right now. Using the table, in step number 4, use the table to answer the question, okay? Use the table. So can I write some wording here? Use the table to find the required could be local maximum, so could be local minimum, okay? So can I just write maximum or minimum? Again, I'm going to show you how to answer the question, okay? To tell me, in this question, we have seen 2 as a location of the absolute maximum, right? Answer the question properly. To answer the question, I'm looking for the location. I'm looking for the 2, okay? I'm looking for the value of the maximum. I will try to tell you how to answer the question, okay? Finally, the function f of x. I don't remember the function. 1 plus 4x minus x squared. That function, okay, has the absolute maximum. In the answer, I'm looking for 2 things, although I only write 1 line, okay? So tell me the location of the maximum. The location is 2, okay? I'm trying to say that is the location, that is 2, okay? And then evaluate the function at 2. So tell me the value of the maximum. The value of the maximum is computed using 1 plus plug 2, the location, into the original function. So do not plug 2 into the derivative. So because it's a critical number, the derivative of the function at 2 has to be 0. So that makes sense? Plug 2 into the original function is 1 plus 4 times 2. And then minus 2 squared, right? Anybody want to tell me this value? It's 9 minus 4. I think it's 5, is that right? It's 5. Again, to answer the question, you tell me the location. You tell me the value. I'm looking for 2 things. Okay, just write 2 triangles. So below the 2 things I'm looking for. Okay, so that's a simple question showing you all the step procedures and probably all the components you need to involve to find absolute maximum or absolute minimum. Okay. Any questions about this? At this point, I want you to recall something, okay? The basic terms. I hope you have some better understanding of the terms. At the beginning, we were trying to define what we mean by local maximum, local minimum. Probably I have a typo somewhere. Why do I have 2 local maximums? So, but I told you the meaning. Okay. Local maximum, local minimum, and then item number 3 and 4 are super useful. You have seen we can use the property of the derivative. I mean the sign of the derivative, positive or negative, to determine the function is increasing or decreasing, right? And then the next important thing is the critical numbers. The critical numbers are possible locations of local maximum or local minimum. Okay. Any questions about this? To do any questions, so differentiate the function first, and then you get the critical numbers by solving the equation of that. Again, the critical numbers are the values of x at which the derivative is 0 or undefined, or DNE, of course. And then from a table, I told you how to form the table. Okay. The row titles are always the same. You label the rows using the same way. Label the columns by dividing the domain using the critical numbers. After you do that properly, it's always safe to use the test numbers to determine the sign. I mean, to complete the second row. Okay. And then you can use the signs to determine if the function is increasing or decreasing on some interval, so that you can answer the question. Okay. All right. If you don't have any questions, we'll work on question 2 for a little bit. For question 2, it's going to be one of the questions on the assignment. I'm not going to go over the detailed solution, but I will give you the key steps until I'm going to tell you the table you need to complete. So we'll get there. Okay. You ready for this? So this time, for these functions, so there's no way for you to use high school math to solve this. You have to use calculus. You treat this function a polynomial of degree 3 as a function defined on the interval from 0 to 6. Okay. Again, we are trying to restrict the domain to the interval from 0 to 6. For this one, I guess I can go over the thing a little bit quicker. Okay. In step A, I'm not going to write the words. So differentiate the function, right? The derivative of the function, simple, right? 144 minus 96x, I think, 96x. So do I get this right? And then plus, so 12x squared. So that's the derivative of the function, which should be simple. Okay. In step 2, we get all possible locations of the maximum or minimum. By that we mean we're trying to get all the critical numbers. We set the derivative to be 0, right? And then we solve the equation for x. And then we have 144 minus 96x, and then plus 12 x squared is equal to 0, right? That's a quadratic equation. To solve an equation like that, you factor the left hand side. Okay. It's probably easier if we cancel out a common factor of 12 first, right? So this one is equivalent to, I'm going to change the order of the terms to write the thing in some nicer form. Okay. I believe the equation is equivalent to x squared minus 96 divided by 12. So anybody want to tell me that? Eight 8x, and then plus 12 equals 0. Sure, thank you. Okay. Again, it's permissible to divide all the terms of the equation by some constant number, non-zero constant. Okay. And then to solve the quadratic equation, you factor the left-hand side. This one is simple. I think you're going to have something like x minus 2 and then times x minus 6 is equal to 0, right? Anybody want to tell me the critical number or the critical numbers? A little tricky. It's probably it's not too tricky. 6 is not a critical number. 2 is a critical number. You see 6 is not in the domain, right? You look at the interval. Okay. So the solution to the equation, the solution to the equation, we have two solutions. We have x equals 2 and x equals 6, but 6 is not in the domain of the function. Okay. We have only one critical number. X equals 2. That's the only critical number. Okay, I did the first step for you. The derivative, I got the critical number for you. Okay. Okay. The next thing we do is to form a table, right? The table is going to be something like. Anybody wants to tell me the first row of the table? The domain of the function is from 0 to 6, and the critical number is 2. Anybody want to tell me how many subintervals in the first row? You could write the first row using the interval notation, or you could use the inequality notation, the same thing. 2 is the critical number, right? So we have two subintervals. I mean, the critical number will divide the interval from 0 to 6 into two subintervals, right? If you do not see it using a number line, okay. But the two subintervals are when x is in between 0 and 2, right? The next one should be when x is in between 2 and 6, right? So we have two subintervals. Okay. And how to label the rows is always the same. The derivative of the function and then the function in these two cells for the two question marks. We need, I mean, for the two question marks, we need the two signs, and also for the last row, you need to determine the function is increasing or decreasing. So can I stop here? I think that's question 3 on the handout. But to make the numbers a little nicer, I will change one number. So can I do the question for the function, now let's say x squared plus 2 over x, the same thing, essentially the same thing, but the numbers are going to be nicer. I hope. I think it's going to be nicer. Okay. That's question 2. Sorry, that's question 3 on the handout. We follow the steps. I will give you the complete solution to this question. On the assignment, you are going to have a similar question to this. So differentiate the function first. 2x, the derivative of 1 over x, I told you to memorize, because you are going to see this over and over again. I told you not before, right? The derivative of 1 over x is negative 1 over x squared. And you differentiate the second term, you leave out the constant of 2, you have negative 2 over x squared. Right? So differentiate the function. We treat the function to have the domain of the open interval from 0 to infinity. Okay. Keep that in mind when we get the critical numbers. You need to make sure the critical numbers is a number on the interval. The next thing we do is to solve for critical numbers. Let the derivative be 0, and then we have 2x minus 2 over x squared equals 0. At this point, you could guess the solution to the equation, or you learned how to solve an equation like that, probably in grade 11. Again, it's permissible to cancel out a common factor, a non-zero constant factor of 2. So the equation of that is equivalent to x minus 1 over x squared is equal to 0. To solve the equation, the way is different from before. I'm going to show you. I believe you can remember this. Okay. This equation is equivalent to x equals 1 over x squared. And then you cross multiply. So do you remember, if you have an equation, so something like a over b equals c over d, under some conditions, under the condition that b and d are not 0, this equation is equivalent to the equation cross multiply, right? AD equals BC. Right. You cross multiply, this equation is equivalent to x times x squared, you have x cubed, and then on the other side you have 1. So do you see that? Cross multiply. Sorry, I do not want to put a big cross in here, but cross multiply, you have this. At this point, you can get the solution on the domain. Now we are looking for what x value on the interval from 0 to infinity. For what x value greater than 0, this equation is satisfied. You see you have only one possible value, right? So x is equal to 1. This is the only critical number. For all the questions we have seen, we have only one critical number. So, but I believe you can imagine it's possible to have more than one critical numbers when the derivative is more complicated, right? Actually, in some cases, you need to deter a critical number. It's possible for a critical number to be an x value at which the derivative is dne does not exist. We mentioned before, right? But in this case, we have only one critical number, right? Now we are ready to form the table. After getting the critical number, we can form the table. In step 3, we form the table, right? The interval, so do you want to use the interval notation or inequality notation? The same thing, okay. Now let's use the inequality notation, okay. One interval is when x is in between 0 and the critical number 1, right? The other interval is the interval when x is greater than 1. You could write less than infinity, but this interval, it means for all the real numbers greater than 1. And then the row titles, I mean how to label the rows, the derivative of the function, right? And then in the next row you'll have the function. In these cells we're looking for the signs in, right? And then we're going to use the signs to determine the function is positive. I mean the function is increasing or decreasing. I think I need the derivative of the function. The derivative of the function is 2x minus 2 over x squared. Anybody want to tell me a test number on that interval, please? You could use any test number. Try to use some nicer numbers. So maybe 0.5, 1/2, right? Now let's use 0.5. Okay. The derivative of the function, I rarely use decimal numbers, but now let's use 0.5. 0.5 is equal to 2 times 0.5 minus 2 over 0.5 squared, so which is 0.25. I don't know this value, so can anybody tell me this value? I believe the first number is 1, and then 2 divided by 0.25, so do you have 8? So the answer should be -7. I do not care about the value, but the sign is negative, right? And then choose a test number on that interval, bigger than 1. Probably you want to choose 2. Okay. And then you evaluate the derivative of the function at 2. So this one should be simpler. So you have 2 times 2, so which is 4, and then minus 2 over 2 squared. This number is positive for sure, I think. So please honestly use the test numbers to determine the signs. I'm trying to say try not to guess. Although in some cases it's possible to guess. After that you say the function. Okay, so this is kind of new. Can anybody try to answer my question? If the derivative is always negative on the interval from 0 to 1, using that information, how can you tell? What can you say about the function? The derivative is negative on the interval from 0 to 1. Using that property, how do you want to tell me about the function? Decreasing, right? When the derivative is always negative, the function is decreasing on the interval. And likewise, the function is increasing when x is to the right of 1. Okay. So we're done step 3. We have completed the table. After completing the table, you see to the left of 1, the function is always decreasing. To the right of 1, the function is always increasing. Right? You see 1 has to be the location of the absolute minimum. So at this point you can say the given function f of x has the absolute minimum. Again, I'm looking for 2 numbers. One number is the location of the minimum. The location is 1, right? So do you see how the table functions? The table exactly is used to convince Originally, after getting the critical numbers, you have seen 1 is a possible location of the absolute minimum in this case. This table is used to convince that 1 is indeed the location of the absolute maximum. Of course, you need to plug this 1 into the original function to get the value of the absolute minimum. X squared plus 2 over x, 1 squared plus 2 over x, over 1, right? So do you have the value of 3? Okay. Again, you don't know how much you have learned. For this question, so there's no way to do this question using high school math. Probably you want to see what's actually going on graphically. I will show you the graph of the function. What's the function again? The function is x squared plus 2 over x. So do you see the function has a local minimum? Actually, you treat the function to be a function defined on the interval from 0 to infinity. You do not look at that branch. Okay. On that interval, the function has the absolute minimum at 1. You see graphically it's true, right? Using calculus, we can actually find this number, and the value of the function is 3. Okay. Any questions about this? Again, 4 steps. So differentiate the function, getting the critical numbers, the second step, and then use a table to confirm the critical numbers you found are indeed the locations of the required absolute maximum or minimum, and then answer the question. Okay. Simple enough. If you don't, we'll move on to the next topic. The next topic is kind of how to find the absolute maximum and the absolute minimum of a function on some closed interval. There's a conclusion you need to know. Okay. I do not have to copy this. So just try to memorize the conclusion. Later on, if we have time, I'm going to tell you more on the y side, but temporarily we concentrate on how. Okay. So just look at item number 8. Okay. The condition, you have a condition. Actually, the condition is that the function has to be continuous on some closed interval. You can treat the thing as you have 2 conditions. One condition is the function is continuous. You know that condition is true for any function that can be written using one formula. So not too rigorously speaking as that. Actually, we have seen a function is continuous on its domain for any elementary functions, right? That's one of the conditions. And the other important condition is that the interval, the given interval, has to be a closed interval. Okay. Under the 2 conditions, the function must have at least one absolute maximum and at least one absolute minimum. Now the following questions are designed to show you how to compute the absolute maximum and the minimum. Okay. We'll use at least one question to show what's going on. So how about we just do this question. Okay. We just do the first question. This time I want to actually, so before we do the question, I want to, to go back to the graph. Again, we have seen before C is a critical number, right? So that's a point at which the derivative is equal to 0. And likewise, D is a critical number. And also B is a critical number. You imagine the function is defined on the closed interval from A to E. Okay. If A and E are included, I'm trying to say, you remember I told you one of the two conditions is that the interval is a closed interval. It means the two endpoints are included, right? If the two endpoints are included, it's possible for the function to return its absolute minimum or maximum at one of the two endpoints. In this particular case, you see the function has the absolute minimum at the left endpoint A. So do you know what I mean? So to do this kind of questions, I mean, if a function is on some closed intervals, you have to take the two endpoints into account. Okay. I will make more comments when we actually do the questions. Okay. Now we actually do the question. Ready? It's kind of the new thing. So before we do the question, I want to convince you the two conditions are satisfied. I mean, the function is indeed continuous on the closed interval, right? The function is a polynomial, right? Which is continuous at any number, at any real number. In particular, it's continuous on the interval from -6 to 6. You do not have to state that. For most functions, the condition is true. Okay. But the next thing I want you to notice, the important condition, is that the interval is indeed a closed interval, which means the two endpoints are included. Okay. For this one, I will write the step procedures in words so that you're going to see what's going on. Okay. Now the solution. When I do the solution, when I make comments, you're going to see everything will make sense. In any case, the first thing you do is to differentiate the function, the derivative of the function. So this one is a little bit long, but super easy, right? The derivative of the function is equal to 6x squared and then plus 18x minus 60. I'm just using the power rule to differentiate the function term by term. Simple, right? In any case, we need to, now you look at the question, we are looking for the absolute minimum and the absolute maximum of the function, which means you need to get all the critical numbers as well, right? The critical numbers, now let's recall, are the possible locations of local minimum, local maximum, absolute minimum, absolute maximum. In any case, we need to get the critical numbers first. Sorry, I told you to write the wording, I forgot. So the first thing you do is to differentiate the function, of course. The second thing we do is to still find all the critical numbers. By setting the derivative to be 0. sorry, I was trying to write 6t. I wrote 6x minus 6t, right? Again, it's permissible to divide the equation by a non-zero constant of 6. After doing that, we have x squared plus 3x minus 10, I believe, right? Is equal to 0. Again, you have a quadratic equation. To solve the quadratic equation, you factor the left-hand side. So do we have x minus 2 and 5? You are looking for two numbers adding to negative 5 and multiplying to negative 5 and adding to 3. So you have x minus 2, right? X plus 5 equals 0. So do I get this right? I think I got this right. Okay, so this time we see one question. We have two critical numbers, actually, right? X equals 2 and these are the critical numbers. Okay. The first two steps are essentially the old stuff, the old thing, right? Now the new thing. Now concentrate. Okay. When the function is on some closed interval, I mean when the domain of the function is a closed interval, we do not form a table. Instead, try to understand me. Okay. Now, what are all the possible locations of the absolute maximum and minimum? We have two critical numbers. These are the possible locations. One possible location is 2. Another possible location is negative 5. Anybody want to tell me two other possible locations? Actually, at this point, we have only 4 possible locations. The critical numbers, 2 and negative 5. And what are two other possible locations? You can tell me the two other numbers. So please, what are the two other possible locations? If you look at the general graph I drew at the beginning of the class, what are the two other possible locations? The two endpoints, right? The two endpoints. If you look at that graph, this function has the absolute minimum at a, which is, yeah. So in this case, you have two other possible locations. Yeah. So you got it right earlier. You have negative 6 and 6. Two other possible locations. I want to repeat the logic. Logically, now if a function is continuous on some closed interval, we have only two types of the possible locations. Can I say two types? One type is the critical numbers. The other type is the two endpoints. In this question, we have only 4 possible locations. So what can we do next? We do not use a table. We do not need a table, actually. We have only 4 possible locations. And then what we do next is to evaluate the function at the 4 possible locations. And then the largest is going to be the absolute maximum. The smallest is the absolute minimum. So does that make sense? without using calculus, you have many candidates to be maximum or the minimum. Any number on the interval is possible, right? But after applying calculus, after getting the critical numbers and using other properties, you see the only candidates to be the locations of the maximum or the minimum are the critical numbers and the two endpoints. Now all we need is to evaluate the function at 4 numbers, right? And then the largest is going to be absolute maximum. Smallest is going to be the absolute minimum. Now in step 3, if the function is defined on some closed interval, how do we proceed? We proceed by evaluating the function at the critical numbers. I forgot the critical numbers already, 2 and -5. Okay. I told you to write the wording. I forgot again. So did I write the wording for the second step? Evaluate the function, the given function. Okay. At the critical numbers. And all the endpoints, the 2 endpoints. Actually, there are only 2 endpoints. So do that first. Okay. Evaluate the function at 2 and -5. And the 2 endpoints, -6 and 6. The given function is a little bit complicated. Can I copy the function to this slide? The given function is that. Now we evaluate the function at four different numbers. Now let's do it together. I need your help, so get your calculator please and tell me. Sorry. Okay, I'm not 100% sure if my numbers are right. You could check later, but the idea is now the idea is the smallest value is the absolute minimum, so probably the minimum is right, and the largest value is the absolute maximum. I told you originally we had many candidates, right? But now we have only 4 candidates. So lastly, identify the absolute maximum and the absolute minimum. Okay. Can I just write some comments here? So this is the absolute minimum of the function on the interval on the closed interval from -6 to 6. Absolute maximum is the largest value, right? So this is the absolute maximum. You see, you have the location, you have the value. Any questions about this? If you want me to summarize a little bit, so be careful of the condition. The function has to be continuous on a closed interval. If that's the case, you can use the following method. Okay. In step 1, you differentiate the function. Okay. In step 2, you get all the critical numbers the same as before. Right. The first two steps are the same. But in this case, when a function is continuous on a closed interval, then the next thing you do is all you need is to evaluate the function at all the critical numbers and at the two endpoints. And then the largest function value will give you the absolute maximum. The least function value will give you the absolute minimum. Simple? Any questions? If you don't, we'll try to take a look at another question. Okay. Actually, on the assignment, you are going to probably do a question very similar to number 2. I'll double check. Yeah, very similar to number 2. And then, and also question number 3 is going to be on the assignment. I will give you some hint. Okay. On number 3. Actually, the question itself, when you do this type of the questions, the idea is easy. So just for some functions, you need to use some other knowledge like trig stuff to get the critical numbers. Okay. It's kind of I'm starting to make comments on the assignment. I will show you the assignment right now. Okay. On the assignment in part 1, you have the Newton's method. We did that on Tuesday. Okay. Probably I'm going to add one more question in the nature. I haven't decided yet. Okay. And then in part 2, the two questions are in the nature that the function is on some interval that may not be closed. You see in question 1, the function is defined on some open interval. In this case, in step 3, you need to form a table. Okay. And for part 2, question number 2, it's also on an open interval. In step 3, you also have to use a table to determine the function is increasing or decreasing on some interval or not. And then you use that information to determine the location of absolute maximum or minimum and so on. Okay. And the two questions in part 3 are in the nature that the function is defined on some closed interval. Okay. Actually, part 3 question 1 is very similar. Actually, so not very similar. You try this question on your own, and then so question 1 is easy. For question 1, so probably I just give you a little bit comment on question 1. Okay. For question 1, so don't be scared. The function is essentially 1/2 times x squared. I mean, in question 1, use a new slide. In question 1, the function is essentially 1/2 times x squared. And then plus 1 over x. I'm trying to say when differentiating the function, so do not use the quotient rule. So this is essentially a number times x squared. You just use the power rule. It's simple to differentiate, right? And then I'm going to make some comments on question 2. I'll probably get you the critical numbers, and then we're done. The derivative of the function. Can you see the screen probably? So should I make it bigger? The derivative of the function for this one, the derivative of x is equal to 1, right? And then the derivative of cos of x is equal to negative side. So the derivative of the whole function is 1 plus 2 times sine of x. I know for some people, whenever you see tricks, you get scared. Okay, and then I told you essentially the same thing. You just need to look for the critical numbers. I think in Math 12, in Pre-Calc 12, you learned how to solve trig equations, right? So that's where you need them. In step 2, we let the derivative be 0, and then we have something like 1 plus 2 sine of x is equal to 0. How to solve the equation for that? For x, I mean. And then I'm going to run a little bit slower, okay? So because I think last year you lost many classes as well. You have 2 sine of x is equal to negative 1. So you have sine of x is equal to negative 1 over, so negative 1 half, right? At this point, so probably you want to recall the graph of the function. Recall the graph of sine of x. Actually, we treat the function to be defined on the interval from negative pi to pi. From negative pi, so negative pi is somewhere in here, and then to pi. So pi is 3 point something, right? Okay. To solve the equation, by that we mean we are looking for x values, so that sine of the x value is negative 1 half. Now let's look at the graph to see how many possible values. Can I draw a horizontal line like y equals negative 1 half? So negative 0.5, the same thing, right? Again, we treat the function to be a function defined on the interval from negative pi to pi. So negative pi is here. So do you see this point? That's negative pi. And the pi is here. So do you see this point? That's pi, right? And then we are looking for all the x values having the condition that the value of sine is negative 1 half. So this point is negative 1 half. So do you see how many solutions? Actually, we are looking for 2 solutions. So do you see the 2 solutions? Actually, it's nice. It's possible for decimals to give you the 2 points. You see the solutions already. So do you? Again, we are looking for x values at which the value of the function is 1 half. That's why I drew a horizontal line. Right. And then you'll see at these 2 points, sine of x value at these 2 points is equal to 1 half. Alternatively, you could use the unit circle. And one other comment. So this point is not included. It's not in the domain, right? this x value of this point is bigger than 5 already. Okay. I think with some computer software or graphing calculator, so they think it's easy. Okay. I think we have seen the solution already. So can I just so write down the solutions? I was trying to use the unit circle, but decimals. So give us the solutions, right? So x value is equal to, you'll see you have 2 points, right? Negative 1 pi over 6. Sorry, I lost the 2 numbers already. Negative pi over 6. And the other solution is x equals to negative 5 pi over 6, I believe. Again, if you want to recall, this part of the knowledge is something you learned in the last year, trig equations. I told you the critical numbers, right? And then all you need is to evaluate the function at the possible locations. Now we have 4 possible locations. The 2 endpoints, negative pi and pi, and also at the 2 critical numbers. You could run the numbers to decimal numbers, and then you use a calculator to evaluate the function at all the possible numbers. The largest will give you the absolute maximum, right? The smallest will give you the absolute minimum.